This photorealistic tracking shot represents the broadcast quality standard of 2026. Every frame maintains absolute structural perfection, from the consistent lighting on the skin to the way the shadows interact with the environment. Achieving this level of stability requires understanding the core paradox of diffusion models. These systems, designed to remove noise from pixels, lack internal object permanence. The AI redraws every single frame from scratch. It has no memory of the pixels it generated a fraction of a second ago, meaning it must reinvent the entire scene 24 times every second. This frame-by-frame amnesia causes character drift and melting artifacts. When a model relies solely on text prompts, it lacks the spatial memory required to keep a character's face or clothing consistent over time. Professional long-form AI video is an output of deterministic pipeline engineering. To eliminate randomness, we use a structured 4-layer generative architecture. This pipeline moves from concept and asset ground truth to motion synthesis and the final output render. Cinematic fidelity is not a lucky accident of the model. It is an outcome dictated by the constraints the creator places on the system. The pipeline starts by feeding a corporate marketing brief into an AI structurer, usually a large language model, to build a discrete, sequential shot list. Because current video models cannot synthesize a complex narrative arc in a single pass, they are used to produce individual, isolated camera shots that are later stitched together. To keep a character recognizable across these separate shots, we use an unchanging identity feature, or UIF. A UIF is a specific, immutable physical trait assigned to a character, like a unique accessory or a distinctive scar. The UIF serves as a mathematical anchor for the diffusion model's predictive weights. It gives the AI a fixed reference point that forces the surrounding pixels to remain stable across different generations. Creators must write rigid character DNA. This description specifies the exact age, skin tone, and wardrobe down to the hex code of the fabric, leaving zero room for the model to interpret the prompt. A diffusion model exploits ambiguity. If a prompt is vague, the AI will hallucinate new, unrequested details for every shot, making character consistency impossible. Rigid character DNA is the mandatory first step in preventing identity drift across a long-form project. In the asset layer, production centers on image-to-video anchoring, or I2V. I2V is a methodology where a static image is provided to the model as a starting frame to dictate the visual composition of the video. The fundamental rule of the asset layer is to never ask the video model to invent the character's appearance. Instead, we generate a character pack. This is a set of static images that serves as the visual ground truth for the subject. A comprehensive reference sheet includes front, side, and close-up views. Stacking these references inside an I2V engine restricts creative freedom, anchoring geometry to reference pixels. This locks identity, keeping character features perfectly static while the environment spins. This rule applies to every change. A new outfit or shift in lighting requires generating a brand new reference anchor to maintain continuity. Visual ground truth overrides the model's tendency to hallucinate, solving the problem of identity drift. The synthesis layer is where we add motion to these locked character assets. This phase requires the separation of identity descriptions from motion descriptions in the text prompt. Because the reference image already defines the character's identity, the prompt should focus exclusively on physics and spatial coordinates. Technical camera strings define the movement. Using terms like orbit left, 50mm lens, or slow dolly in allows for precise control over the virtual cinematography. Character motion must be kept small and readable. High-intensity movements often break the model's anatomical logic, leading to warped limbs or distorted faces. For complex physical actions, we use keyframe interpolation. This is the process of generating a video sequence by providing the AI with a starting frame and an ending frame, and having it calculate the motion in between. By setting these specific visual goalposts, the AI is forced to follow a strict mathematical path between two known states. Stripping identity data from the text prompt and relying on visual endpoints forces the AI to operate as a deterministic physics engine. The output layer involves the hard requirements for rendering, particularly for open-source models like LTX2. Cinematic fidelity requires adhering to strict mathematical constraints during the rendering process. For successful rendering, output dimensions must be divisible by 32, and the frame count divisible by 8 plus 1. Breaking these mathematical rules causes padding errors and breaks tensor calculation efficiency, disrupting how pixels are organized over time. While drafts are rendered in flat 720p SDR for speed, the final export uses rich HDR, or high dynamic range. HDR allows for physically accurate light reflections and superior color depth in the final pixels. We manage high VRAM loads through NVFP8 quantization. NVFP8 is a high-efficiency floating point format used to store model weights, reducing the memory footprint by 30% while maintaining clarity. Cinematic rendering is an engineered mathematical outcome that requires exact numerical compliance. This modular workflow brings broadcast-quality AI video into reach. Professional output is achieved by chaining specialized models together. A flowchart moves from the brief to the reference stack, into motion strings, and through the render engine. Final polish happens in post-production, where neural engines upscale the output to a sharp 4K finish. Creative control in 2026 is the result of applying these technical constraints. The pipeline emphasizes the role of the systems architect, a creator who dictates rules to the AI, rather than manually adjusting individual pixels. Predictability is engineered through reference stacking and adhering to exact mathematical rendering parameters. Mastering the modular pipeline provides full control over the final output. Mastering these layers allows for the creation of cinematic, long-form content that maintains flawless consistency from the first frame to the last.
Hey everyone, welcome back. Subscribe to AI Skills Learn for more awesome content. And don't forget to like and share this video.